So far, we've been looking at data which is binomial, where each element of my sample gives me a response that fits into one of two categories, success or failure, true or false, that sort of thing. But suppose responses are not binomial. Suppose they fit into more than two categories, like three or more categories. What if I do a survey and ask, what's your favorite brand of soda pop? Coke, Pepsi, Mountain Dew, whatever, that sort of thing. Well, suppose I ask, what state are you from? Suppose I ask, what is your favorite type of pet? Dog, cat, fish, bird, whatever, that sort of thing. Now, my data isn't going to be binomial, fitting into one of two categories, but I can put my data now into one of several categories. Let's work through an example about this. We can analyze this sort of data and compare this sort of data with a null hypothesis using what we call the chi-squared distribution. All right, so here's a scenario. Suppose I have an ordinary die, a six-sided die, and I'm concerned that this die has been loaded in some way so that's unfair. It rolls, in this case, more sixes than it should. What do I want to do? Well, let's roll this die out. Suppose I take this die and I want to test it out to see if I get more sixes than I think I should happen normally. So I roll the die 42 different times to test it out. I keep track of all these in a table, and then I compare it with my expectations. Okay, so what would I expect a normal die, a fair die, to be? That gives me my null hypothesis in this case. If the die is fair, then there's going to be a 1 in 6 chance of rolling each number, a 1/6 probability of each of the different outcomes. And so there's my null hypothesis. The alternative is going to be the probabilities are not all 1/6. There's something else. So the first thing I need to do is figure out, well, what would I expect if the die was fair? How many 1s would I expect to get? How many 2s? How many 3s? Well, those are all equal. So 1/6 of 42 rolls is 7. I would expect to have exactly 7 1s, 7 2s, 7 3s, 7 4s, 7 5s, 7 6s, except not exactly that number. I would expect them to vary a little bit, right? I'm going to do, it's a random experiment, but I would expect them to be somewhere in that number. So all those 7s, those are my expected values. So then suppose we do the experiment. Suppose I roll 6 1s, 7 2s, but only 5 3s, 7 4s, 5 5s, and suppose I roll 12 6s. Now that looks a little bit fishy to me. That's a little suspicious. Would I get a result like that? That seems, 12 6s, really? Would this result be very unlikely if the die was fair? We're going to run a hypothesis test, just like we've been doing before, except slightly different mathematics behind it. But the underlying logic is the same. We need a p-value that will measure how unlikely a result like that would be if the die was fair. All right, so we're going to come up with a test statistic, but this is going to be a new kind of test statistic. Instead of a normally distributed test statistic like we've been studying in the past, now we're going to get a chi-squared test statistic. It's going to follow a distribution that we can study and measure and quantify, but we got to do it in a different way. So here's what we do. For each of these 6 categories, I take my observed value, I subtract my expected value to get the difference between those, and then I square it, because I don't care if they differ in a positive sense or a negative sense. I don't care if my observed value is bigger than the expected or the expected is bigger than the observed. I'm just looking for differences. If these two things are different than each other, I want to know about this. So I do observed minus expected, find that difference, and then I square it. So when you square something, multiply it by itself, negatives become positive. So all the results are going to be positive, and then I divide that by the expected value. So in the first case, I would expect 7 1s. I only got 6 of them. So I do observed minus expected, 6 minus 7. Well, it's a difference of -1. -1 squared is +1. Then I divide it by my expected value, which was 7. And then I do this for each of my 6 categories. So for the 1s, I got 1/7. For the 2s, well, the expected is 7 and the observed is 7. So 7 minus 7 is 0, so there's nothing there. For the 3s, I expected to get 7 of them, but I only observed 5 of them. Only in 5 of my 42 rolls did I get 3. So 5 minus 7 is -2. -2 squared is +4. So I got 4/7 for my sum there. In terms of 4s, no, that one's fine. I expected 7. I got 7. There's going to be a difference of 0 there. In terms of 5s, oh, yeah, there's another one. I expected 7. I only got 5. 5 minus 7 is -2. -2 squared is +4. I got 4/7 from that one. And then here's my weird one. On the 6s, I expected, based on my null hypothesis, that this would be a fair dice. I expected only to get 7 sixes? I got 12 of them. 12 minus 7 is 5. 5 squared is 25, so I have 25 sevenths. So then I add up all these things and I get 34 sevenths, which is about 4.86. If we did this many, many times with a fair die, assuming that the null hypothesis is true, then this test statistic, this chi-squared test statistic, would follow what we call a chi-squared distribution. So we need to know about what's the chi-squared distribution? What does it look like? Here's the chi-squared distribution, or, well, here are several chi-squared distributions. First thing we need to know is that this is a strictly positive distribution. You can never get a negative number from this because, well, expected values are always positive, and whenever you square anything, you get positive. So we're always adding up a bunch of positive numbers. So all of these chi-squared test statistics are all positive numbers. And the next thing we need to know, okay, so I mean, that's different than the normal distribution, which can be positive or negative or zero. The next thing we need to know is that, well, there are many chi-squared distributions. There isn't just one, depending on how many categories we have. I'm going to get one distribution if I'm rolling a 6-sided die, and I'm going to get a different distribution if I was rolling an 8-sided die or a 4-sided die or any of those sorts of things. So there are many, many different chi-squared distributions depending on the number of categories we're working with. So we take the number of categories we have, we subtract one from it, and we get a number we call the degrees of freedom in this case. Essentially, in this case, if I start, I say, okay, I'm going to roll up 42 times, and here's how many ones I got, here's how many twos I got, here's how many threes I got. Well, by the time I get up to 5, you can figure out what the sixth one must be because, well, that's the only one that's left. So that's what we mean when we say degrees of freedom in this case. So in this case, we had 6 categories. We have 5 degrees of freedom. So in this case, that's what we have. Now, in order to apply this model, so this method of analyzing data only applies, first of all the expected values must be at least about 5. If they're less than 5, well, this method doesn't really work. So always make sure that you've got at least, you expect to have at least 5 counts in each category. As always, each thing must be independent of all other things. So, for instance, if I'm surveying people about their favorite brand of soda pop, and people are lined up in a line with their friends, well, maybe friends would all prefer Pepsi or something like this. Maybe they all have similar preferences. So each individual element of the sample must be independent of each other independent element of the sample. There can't be any correlation between those. Otherwise, all this method of analysis goes right out the window. All right, so now we know something about this crazy chi-squared distribution. I need to use that distribution to get my p-value. I want to know what's the probability that we would get 4.86, in this case that's what we got, or more extreme, more interesting, assuming that the null hypothesis is true and that this is a fair die. So remember, this chi-squared test statistic, that's a measure of how different my observed and expected values are away from each other. If they were all to be the same numbers, if I got exactly what my expected values were as my observed, if I got 7s in each case, my chi-squared test statistic would be 0. That would be perfect agreement between observed and expected. And then this describes how different things are likely to be. The more different they are, the farther my observed and expected are from each other. That's going to give me a bigger, a more positive, a larger value of chi-squared. Because remember, I'm doing this crazy squared thing. Whenever I square a number, whether positive or negative, I'm always going to get something bigger. I'm going to get something positive out of that. And so I'm always going to do a right-tailed, a one-sided test on this. What's the probability of getting this or more? So in this case, I want the probability of getting a chi-squared test statistic of 4.86 on 5 degrees of freedom. Fortunately, my good friend R knows all about the chi-squared distribution. So let's see. Remember, in R, it's always the default is to give me the probability of this value or less. I want that value or more. So I need to do 1 minus. In this case, 1 minus PCHISQ of 4.86 comma 5. There's my degrees of freedom. And in this case, R tells me I have 0.433. 43.3% is my p-value. So what conclusions can I draw from this? What can I learn? Well, that's not really unlikely. That's, again, we're dealing with a different distribution here, but the fundamental logic is still the same. I look at these results and I say, would these results be fantastically, wickedly, ridiculously unlikely if the null hypothesis was true? And in this case, I say, not really. Let's assume alpha is 5%. There's a typical threshold. No, are we below that? No, not by a long shot. 43.3% is larger than 5%. My p-value is larger than alpha, so therefore, this is not an unlikely result. Results like this, similar to this sort of thing, would actually be pretty common. If I have a fair, normal, typical, average, ordinary die with a 1 in 6 chance of rolling each thing. Therefore, well, we don't accept the null hypothesis. Remember, we never accept the null hypothesis. So we cannot conclude that the die is fair. That would be what the null hypothesis says. But instead we say, well, this difference, this discrepancy is not statistically significant. We fail to reject the null hypothesis, meaning, in this case, we don't have evidence indicating that the die is unfair. Again, that doesn't mean it's fair. Maybe it is. That's possible. Or maybe I just don't have enough data. Maybe if I rolled that crazy die 100 times, maybe that would detect the unfairness of the die. Now, that's why we never accept the null hypothesis. We never know whether the null hypothesis is true, or maybe it's close, or maybe we just don't have enough data to bring that out to demonstrate that it is untrue. So in this case, we really don't learn anything about the situation. This data does not demonstrate that the die is unfair. All right, quick summary. So sometimes we're out there gathering data in data land and we find that each data point fits into one of 3 or more categories. So what do? Well, we count up the number of data points. How many counts do we have in each of these bins, however many they are? In this case, we have some sort of a model which gives us our null hypothesis, some sort of expectation. And then we've got a discrepancy between what we observe and what we expect to see. And then we want to see, is that discrepancy statistically significant or not? So we compare the observed number of counts in each bin with the expected number of counts in each bin. Our test statistic comes from this lovely little formula where in each case we subtract observed minus expected, we square it, we divide by expected, and then we add that up for each one of the categories we have. We find that the result will be follow a chi-squared distribution. If the null hypothesis is true, the result will follow a chi-squared distribution with k minus 1, categories minus 1 degrees of freedom, because there's a whole bunch of these chi-squared distributions out there, each for a different number of degrees of freedom. And then we use the chi-squared distribution to find our p-value. Our p-value tells us what's the probability of getting this or more extreme if the null hypothesis is true. So we evaluate whether this discrepancy between observed and expected, is this the sort of thing which would be likely to occur by random chance, or is this going to be a really unlikely sort of thing? And in that case, could we conclude that we reject the null hypothesis? Or, as we did in this case, can we fail to reject the null hypothesis because our results were not terribly unlikely?